But just a fun little thing for today. But switching gears, we now are going to go back to talking about the lives of stars, as well as just how we can measure distances to stars, ages of stars, all these other kind of fun things. So just as a reminder, what we were talking about last class was how smaller stars end their lives. So these are stars that are going to be similar size to the sun or smaller, where they will fuse hydrogen for most of their life. You guys did some calculations to see what that would look like. After they fuse hydrogen, when they run out of hydrogen, they'll expand to red giants as their core contracts until it's hot enough to fuse helium. Then they will fuse helium for a while until they run out of helium to fuse into carbon and oxygen in their cores. And when that happens, the cores will not collapse. They won't get hot enough for these smaller stars to fuse heat, carbon, and oxygen into heavier elements. So there won't be fusion happening in the core. And as we discussed, stars need fusion. So they will run out of fuel to fuse. They'll run out of helium to fuse into carbon and oxygen, and they will start to die. So as they die, we get things like pretty planetary nebulas, like the Ring Nebula, where there's the small white dwarf star in the center, and then the outer layers, which have expanded away over time. So this was the image we ended with last class, as we discussed the lives of medium-sized stars. High mass stars are going to do similar things, but it will look slightly different. So these are stars that are about 8 times as massive as the sun. So the O, B, and A stars we talked about when you guys made your own stellar classification systems and then compared that to what astronomers do. These are those bluest stars, so the O and B stars, as well as some of the A stars. They'll start their lives kind of similarly, burning hydrogen into helium. Again, like you all calculated for what's happening in the sun. But when they run out of hydrogen and their core starts to collapse, it will be easier for their cores to get hot enough to fuse helium fairly quickly. So they'll start fusing helium throughout their core. Because they're bigger, there's more mass, there's just more stuff for it to press together and get the temperature and density conditions you need to fuse helium in the core. Eventually, these stars will also run out of helium, but when they run out of helium, it will get hot enough to fuse carbon and oxygen into heavier elements in their core. So when that happens, you'll end up with a sort of onion-like structure in the core of these stars. Sorry. My pointer. So in the center, you'll have your heaviest elements. We'll end up with iron in the center. So an iron core, you can't fuse heavier than iron. And then in and out, we'll get layers of lighter and lighter elements as you move out. So I like to think of this as kind of like an onion star because it has lots of layers of different elements as you move out. Once you get to iron in the core, we can't fuse to heavier elements than iron. So the stars will stop doing fusion in the core, and that will be the end of these massive stars' lives. We'll talk more about stellar death next week before we get to our test. So that'll be our last kind of topic. So just to show this on our HR diagram, what this looks like. So we had the main sequence, which is where most of our stars are going to be. And that's where stars are going to spend most of their lives. That's where we're burning hydrogen into helium. As they evolve and they run out of helium to fuse into hydrogen, they run out of hydrogen to fuse into helium, sorry. They will evolve off the main sequence, expanding to become giants, supergiants, or red giants, depending on what kind of star they are. And they'll kind of move back and forth across the red giant, across the supergiant branch as they change what elements are being fused in their core. Another thing we can look at another thing we mentioned is that for most of a star's life, it will be on the main sequence. So most of a star's life, no matter how massive it is, it will be burning hydrogen to helium. The rest of the steps will happen fairly quickly. For example, a star 20 times as massive as the sun will spend about 7 million years fusing hydrogen to helium. Then it will only spend 500,000 years fusing helium to carbon and oxygen. Once it runs out of helium, it will be fusing carbon for about 600 years. When it runs out of carbon, it will fuse neon for about 1 year, oxygen for about 6 months, and then silicon for only 1 day. So once you run out of hydrogen, stars are pretty much done with their lives. They move through the rest of the elements fairly quickly before dying. And this is also a very massive star, so it has that smaller lifespan than our sun did, which we kind of looked at. We looked at how you could calculate that last class, where stars with more mass have more fuel to burn, but they're also burning through their fuel very, very quickly, which means they don't live very long. So 7 million years is pretty short compared to that 9 billion years that the sun will live. One really cool way we can get the ages of a lot of stars is by looking for star clusters. There was a question I missed. So there was a question, just a reminder about the test. The test is next Thursday. So that will be when it becomes available. But just like the previous test, you'll have a week to do it. So it will become available next Thursday, and then you'll have a week to complete it. Sorry, missed that question. Any other questions about anything so far? Okay. So back to star clusters. So when we're talking about the ages of stars, briefly when we started this, we talked about how stars form out of clouds of gas. And one cloud of gas will form many stars. So stars will form kind of in groups. And the really nice thing about looking at these groups of stars is that we know they all probably formed about the same time. So if you find a group of stars all together, they formed out of the same cloud of gas, and that means they all formed around the same time and are all going to be the same age. So we can use star clusters to look at how different spectral classes of stars age over age, because we know they're all the same age in that cluster. So that's one of the ways that we can tell that O and B stars don't live as long as the lower mass FGK stars. We can also use different clusters at different ages to get an idea of how stars age over time. So we can compare stars within clusters to see how different stars age, and then we can compare star clusters to see how stars in general change over time. There's a few different types of clusters that we can look at, so that's what I'm going to talk about now. The first is going to be stellar associations. So these are going to be the youngest groups of stars, so just formed out of gas and dust, or gas and nebula. The light from these clusters is going to be dominated by just a few O and B stars. So these clusters will be young enough that the O and B stars haven't moved off the main sequence. And because O and B stars are just so much brighter than any other type of star, they will dominate the amount of light coming from these stellar associations. Even though there's way more K and M stars, even though there's always going to be way more of those low mass stars, they will be so much fainter that the light from a stellar association will be mostly from O and B stars. As we get slightly older, the next type of cluster we'll look at are open clusters. So these are just slightly older groups of stars, but we're still pretty young. There's still going to be some gas present in these clusters. So from when the stars formed, there will still be some of that gas cloud still left. And there's still going to be a lot of kind of the blue spectral class stars. So maybe some of the O stars have died, but we still have B stars, or maybe the O and B stars have died, but we're still getting a lot of light from A stars. So they're good for studying large stars still on the main sequence. So this is also kind of relates to your HR diagram lab, where you're going to look at an open cluster and see where it falls on the HR diagram. So that's something this weekend, if you want to earn some more lab points, the HR diagram lab looks at open clusters and how we can get ages by plotting where stars in an open cluster fall on the HR diagram. The last kind of cluster we'll talk about are globular clusters. So these are dense groups of old stars. So there's no more O and B stars present in globular clusters because they have all died. So globular clusters are going to be the oldest groups of stars that we can see. And instead of being dominated by light from O and B stars, we're going to begin to actually see the fainter stars because there are no O and B stars left. They've all run out of fuel. They've lived fast, die young, and exploded and left us with a bunch of these smaller mass stars that live forever. Globular clusters are big enough that they are actually held together by gravity, so they won't get pulled apart as they move around our galaxy. And they only tend to exist in the outer edges of galaxies. So when we start our next badge, we'll talk more about the structures of galaxies and how we measure that and how we can use globular clusters to actually study where we are within our galaxy. Another thing that's kind of cool about globular clusters is because the stars in them are so old, they have fewer heavy elements. So anything outside of hydrogen and helium, we said, is going to be a metal or a heavier element. Because we need stars to create these heavy elements, since globular clusters formed when there hadn't been stars to create heavy elements. So the stars in a globular cluster are going to be more, even more hydrogen and helium than the stars we see around us in the area around the sun. So just a kind of cool thing to think about, how these older stars have a slightly different composition than the younger stars around us. Any questions about the three types of clusters? Are really young stellar associations, still pretty young open clusters, and then our really old globular clusters. And if you want to practice with these a little bit more, the HR diagram lab is a great place to check out clusters. Okay. And as I mentioned, we can kind of use where stars fall on the HR diagram to figure out the age of a cluster. And we do that by looking for which stars in the cluster are no longer on the main sequence. So if you can find the lowest mass star that has run out of hydrogen to fuse into helium, you know how long that star will live, so that will tell you the age of the cluster. So if you look at a cluster and you see all the O and B stars have died, you know that cluster must be old enough that all of its O and B stars have died. If you look at a cluster and you don't measure any A stars either, then you know that all the A stars have also used up all their fuel and died. So the cluster must be at least the age of A stars, so a few billion years. So the way that we can view this is we can see this is our HR diagram again, where we have temperature or spectral class or color on our x-axis, and then luminosity, brightness on our y-axis. And here we have the kind of main sequence, this thick purple line plotted here. And they've shown different clusters on this HR diagram. So the ones that still seem to be pretty much just following the main sequence, those are going to be our youngest clusters. So the youngest cluster shown here is going to be NGC 2362. And then we can see, okay, H and Chi Persei still looks pretty young, but maybe some of its O and B stars have run out of hydrogen. So we can look at which color, which spectral class of star is no longer on the main sequence to get an idea of the age of the cluster. And the further down the main sequence, the turnoff point is, the older a cluster is. So the oldest cluster here we have is M67, which is probably a globular cluster where it's lived long enough that even stars around the same size of the sun are beginning to die. So this, the M67 cluster is probably pretty close to 9 billion years old, whereas NGC 2362 might only be a few million years old. So we can use where this turnoff point is to get an idea of the age of a cluster. And then we can use looking at different clusters to figure out how stars age over time. So this is one of the main ways we can learn something about stars, learn about the lives of stars just by looking at where they fall on an HR diagram. And just to kind of show this one more way, this is, I think we're hit it kind of at a bad point. Let's let it reset itself. But this is just showing how a star cluster will move across the HR diagram with time. So up here we have time moving forward in billions of years. And then they're also showing what a different solar mass star will be doing. So a 22.6 solar mass star, a 1 solar mass star, and a 0.7 solar mass star. And what you can see is with time, the more massive stars are aging off of the main sequence and either going through giant phases or potentially ending up as white dwarfs. Because the O and B stars don't live very long, there's not going to be many stars up in this portion of the graph, in this portion of the HR diagram, for very long at all. So this is just, again, showing how the stars in a star cluster will age over time and how we'll get the most massive stars dying fairly quickly, where the lowest mass stars will hang out forever on the main sequence. So before we switch gears and start talking about how we measure the distances to stars and the masses and radii of stars, does anyone have any questions about this, any of this, using HR diagrams to measure ages? Okay, and I'll do one last plug for the HR diagram lab, where you will actually do this process, act as an astronomer measuring the age of a cluster. Okay. So now we're going to focus on, instead thinking about the lives of stars, we're going to think about how we can measure the mass, radii, and distances to stars. So far we've been kind of just looking at the light, the color, and the spectra of stars, and now we're going to think more about what else might we want to know about stars and how could we go about getting these measurements. So the first thing I want to talk about is distances. And this is really important because if we want to really find out if we want to find out where a star is on an HR diagram, you need to know its luminosity, which is going to depend on distance. So if all stars were the same brightness, then the stars that looked brightest would be the closest stars. The stars that looked dimmer would be further away. But unfortunately, not all stars are the same brightness. So the brightness, stars that look bright in the sky might be actually really bright stars, or they could be just really close stars. So we need a way of figuring out the actual distances to stars so we can separate stars that look bright because they are close and stars that look bright because they are bright. So figuring that out is really important if we want to measure the different properties of stars. So we need to find ways to measure distances besides, we can actually start to get the actual brightnesses of stars. We can understand what those are. The first way we can measure distances to stars is by using something called parallax shifting. So that's this works only for the closest by stars, but is the first way that we're able to get distances to stars besides our sun. So you need something close enough that as we rotate around the Earth, we'll see the nearby stars shift with respect to more distant stars. So the way that we can all practice this ourselves is you can hold out your arm, you can give me a thumbs up. If you're on Zoom, I can see you giving me a thumbs up. And as you blink your eyes, your thumb should look like it's jumping back and forth on the computer screen. So you should be able to see your thumb move with respect to the more distant things behind it. And that's kind of a parallax shift. Your thumb is jumping back and forth, changing position. And if you held it closer, the jump your thumb would move would be bigger. If you hold your arm further away, it's going to be a smaller jump. So on my screen, when I close my eyes, I can either cover up the X in parallax or I can cover up the P in parallax, depending on which eye I have open. And if my thumb is closer, it's a bigger jump. I can almost cross the entire slide. So we can do that with stars as well. As we move around the sun, the Earth changes position, and we can see how stars move, nearby stars move with respect to distant stars. So as the Earth rotates around the sun, you can think of the different positions on the Earth, as kind of your two eyes. So the Earth may be in June and the Earth in December. And as it looks at a star, a nearby star, that star will shift position depending on the time of year you're looking at it. So we can use that shift in position along with just a little bit of trigonometry to find out the distance to a star. And we come up with this pretty nice equation where the distance to a star measured in a unit called a parsec is going to be equal to 1 divided by the parallax shift when we measure our parallax shift in arc seconds. So really pretty easy equation to remember, just distance equals 1 over parallax shift. So just as a quick reminder, an arc second, so if we measure angles, you can think you have 1 degree, there are 360 degrees in a circle. There are 60 arc minutes in 1 degree, so 60 arc minutes, if we split up our degree into 60 bits, you would get 60 arc minutes would be 1 degree. And if you take that arc minute and you split it further into 60 again, you get 60 arc seconds in every arc minute, 60 arc minutes in every 1 degree. So this is just an angular measurement. Just because stars are so far away, we need to introduce these really, 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 really small angles to actually measure the distances, the parallax shifts of the nearest stars. With that in mind about what an arc second is, we can now define a new unit called a parsec. So this is where why astronomers get frustrated when they watch Star Wars. And Han Solo said he does the Kessel Run in 12 parsecs or whatever. It's like a parsec isn't a unit of time, it's a unit of distance. That doesn't really make sense unless he's somehow weaving around asteroids. Anyways, sorry, that's my little rant. But that's if you want to annoy an astronomer, you can use parsec as a unit of time and they'll get frustrated because it's a unit of distance. So a star with a parallax shift of 1 arc second will be exactly 1 parsec away. So that's how we define the parsec. It's the distance to a star that would have a parallax shift of 1 arc second. So just as a little test to see how we're doing, if we remember that our equation for parallax shift, we had d equals 1 over p. So if the nearest star is 1.3 parsecs away, how much of a parallax shift should it have? So this is going to be a little bit of math. Once you get your number, if you could put it in the chat so we can check to see how we're doing. Yeah, so question about the values. So we have our closest star is 1.3 parsecs away. So 301 technically. And we want to find, so we know distance, we know this big D, we want to find little p. So our parallax shift, little p, when we have a distance of 1.301 parsecs. Yeah, so it's going to be a parallax shift of about 0.77 arc seconds. So great. And just kind of like a fun little historical story. So Aristotle, back ancient Greece times, Aristotle argued that the Earth must be the center of the universe because he did not measure any parallax shifts. So he looked at all the stars and said, okay, if this Earth was rotating around the sun, we would expect to see these nearby stars shifting over time. And we don't, so therefore the Earth must not be going around the sun. So all of his science was right. The problem was he did not have the ability to measure parallax shifts of 0.77 arc seconds. That is a very, very small shift. So the problem was he did not realize that the nearest stars were so far away that even if they were shifting, we would need better instruments than just a human eye to actually measure it. So just kind of a fun thing to think about with science is like, you can have all of your science right and come to the wrong conclusion depending on what your observation, how great your observations are. So just a way, like, as we get better and better observations, now we have a space telescope called Gaia that is measuring the parallax shifts of stars to 0.1 micro arc seconds. So really just incredible measurements to get a better idea of how stars are, where how the distance is the nearest stars, and use parallax shifting to actually measure that really well. So as we get better equipment, we can do this even better, and we can see that yes, stars are shifting. They are just so far away that the parallax shifts are very small. Any questions about that before we move on? There's another lab that you can do. You can actually measure distances. So there's a parallax lab that you all can do. Might be a good one to do over the weekend because it takes a little longer, but you can measure the distance to objects actually around your neighborhood by looking at how they shift as you move back and forth in space. So another option for a way to earn lab points as we wrap up the Stellar Science Badge. So as we talk about measuring distances, we can also sometimes sort of use the inverse square law. So we talked about this when we talked about light, and a lot of you made your own measurements of the inverse square law in the inverse square law lab, where we can see that more distant, the further away an object is, the dimmer it looks, and that brightness changes as 1 over d squared. But in order to think about how we can use the inverse square law, we need to also think about how we measure brightness. So the way that astronomers often measure brightness is using something called the magnitude system. The brightness an object looks would be its apparent brightness, apparent magnitude. Unfortunately, because astronomers are the worst, the magnitude systems is backwards. So the lower a magnitude you have, the brighter you are. So if you have a negative magnitude, you're really bright. If you have a positive magnitude, you're getting pretty dim. So for example, the sun has a magnitude, the sun's gonna be the brightest thing in our sky. It has a magnitude of -26. The moon is about -13, so fainter than the sun, but still pretty bright. Venus is about -4.4, so typically one of the brightest things in our sky, brightest stars in our sky is going to be Venus, which is of course a planet, but it looks like the brightest object in the sky besides the sun and the moon, and it's about -4.4. And then A stars end up around 0, but that would be, depends on how far away they are. So again, magnitudes is how astronomers often measure brightness, but they're backwards. So negative is really bright, and positive is going to be very faint. If We can measure the apparent magnitude. In order to get a distance, we also need to know the absolute magnitude, or how bright the object is if you were 10 parsecs away. So the apparent magnitude is how bright the object looks. The absolute magnitude is a measurement of how bright the object is. So independent of distance. So we define absolute magnitude to be how bright an object would appear if it was exactly 10 parsecs away from Earth. So for example, the sun, because it's a lot less than 10 parsecs away from Earth, it's only 1 AU, which is about 1/200,000th of a parsec around. So the sun has an apparent magnitude of -26, but it would have an absolute magnitude. If the sun was 10 parsecs away, it would have a magnitude of 4.7. So a lot fainter, higher in the magnitude system, a lot fainter. On the other hand, Betelgeuse, one of the brighter stars in our sky, has an apparent magnitude of 0.5. So it looks like it has a magnitude of 0.5. If it was 10 parsecs away from us, it would have a magnitude of -7.2. So it would be much, much brighter. Because it's actually further away than 10 parsecs, it looks fainter. And we can use that difference. We can compare the difference between the apparent magnitude of a star and the absolute magnitude of a star to figure out the distance to that star using our inverse square law relationship for how light fades with distance. But in order for this to work, we need to know the absolute magnitude of the star we're looking at, which is kind of the biggest problem here. So if we know how bright a star is, and we can compare it to how bright the star looks, then we can find a distance. So one of the ways we can figure out how bright a star actually is by exploiting some of the relationships that we measure in variable stars. So a variable star is going to be any star that changes brightness with time. Pretty much every star is going to change brightness at some point of time, but variable stars are typically stars that have changes of brightness that we can measure, and we can use those changes to figure out what type of star it is and how bright the star is. So very useful for getting this kind of difference between absolute and apparent magnitude. A quick note, sometimes you will look at stars and they will look like they're changing brightness. This is typically not because they're variable, it's because the star's light is passing through Earth's atmosphere, and Earth's atmosphere flows around and moves a bit, so we see stars twinkling. That's not the variability of stars, that's the variability of Earth's atmosphere. So the period of variation for stars is going to be longer than what is easy to observe just by eye. You actually have to get multiple days of observations to measure the variability of stars. One of the most useful kind of variable stars is a type called Cepheid variable stars. So these are stars that get brighter and dimmer as they age off of the main sequence. So as they're running out of hydrogen to burn, the properties of their core are changing as they start to burn helium, and that causes them to start to kind of pulse a little bit. They move out of hydrostatic equilibrium, so radiation pressure and gravity are no longer balancing, and they start to expand and contract. As they expand and contract, they change brightness, and they do this in a pretty regular way, which is really nice. So I've got a little toy model of a Cepheid variable here. So the Cepheid variable starts out nice and hot and contracted, and then as it starts to fuse helium, the core gets really hot, and the radiation pressure increases. So the star gravity and radiation pressure aren't balanced, and the star starts to expand. Eventually, things will cool down enough because the star is expanding that the radiation pressure will decrease, and gravity will start to cause the star to collapse until it collapses so much that radiation pressure takes over again, and we get these pulsations as the Cepheid changes what's happening in its core. So it expands and contracts as the balance between radiation pressure and gravity no longer stay in balance. when the star is largest, so when the star has expanded out a lot, we're seeing an outer cooler layer. So even though the core is really hot, the outer layer is really cool and the star will look dimmer. When the star is contracted and hot, we are seeing the star as well, it's hotter, and we're seeing the star will increase in brightness. So as it pulses, it's not just changing in size, it's also changing in brightness. So as we get really big, the star is dimmer, so we have a higher magnitude. As we collapse, the star is brighter, so we have a lower magnitude. And this occurs for over a period of a few days, depending on the size of the Cepheid variable we have. So you can measure the period of pulsations on Cepheid variables by looking at the different peaks and measuring the time it takes between two of these peaks. And that will be the period of your Cepheid, the time it takes for it to expand and then contract and expand. So one expansion, one getting smaller and then bigger again would be one period. So we can measure that, and using that, we can find some nice relationships between the period and the luminosity, which is what you guys are going to do now. So this is our assignment for day 13. So in our Canvas page, you should see something called day 13, variable stars and the distance to stars. In that, hopefully all of these things are published this time. There's a few questions like normal, but the main thing we're going to do, you're going to make a plot, which we've done a few times before, of period versus magnitude for some Cepheid variables. And then you're going to use that plot to estimate the magnitude of a few observations of Cepheid variables. So that's our in-class assignment for today. As I open up breakout rooms, does anyone have any questions? Okay. Like normal, I'll be around to bug you and answer questions as you work through this. So let's try to take around 15 minutes or so to work through this, and I will be around to answer questions as we do.